So here is a clearer picture that is drawn, a clearer PowerPoint picture drawn, so it's easier to understand. And let me just walk through the various signals that I have in this and see if this really works. So I have a VI of t, that's my music, and that gets converted to ID of t, and that's the current through the light emitting export dweeb, and then that gets converted to light. That light goes and impinges on the photo receiver, and it produces a current IR of t, and that then gets amplified, and I produce some sound through some kind of a speaker system. So let's take a look at this little sort of transfers that are happening. And what is interesting here is that based on my assumptions, where I've said the intensity of light is proportional to ID coming out, and the intensity of light impinging on the photoreceiver, XR, will be directly proportional to the current that comes out of it. So in that case, I have several components here which are linear. So ID turning into light is linear. Okay, I've told you that light intensity is proportional to ID. And similarly, I've told you that the conversion from light intensity on the photoreceiver to the current, I've told you that is linear. And why don't I also tell you that the current I gets turned into sound and through a linear amplifier. Okay, so my amplifier is a linear amplifier, and so that gets turned into sound. Oh, and by the way, we'll learn how to build amplifiers pretty soon in this course. So all this seems pretty good, except for one thing. Okay, notice that this piece here, VI getting converted to ID, this is nonlinear. Okay, that is the problem. So everything is linear, save for this piece here, where my conversion from VI to ID is nonlinear. And the reason is that for this export dweeb, the equation that I have is my good old equation. ID is A e raised to b Vd. Okay, so given that equation, the conversion from Vd to Vi is nonlinear. Okay, notice that in this case, Vi is the same as Vd. Okay, the node voltage here is Vi, which is equal to the node voltage here Vd. Okay, the two are the same. So given that, Vi to ID conversion is nonlinear because my device is nonlinear, and that is a problem. Okay, and what that will do is that will lead to distortion. A problem is that this is nonlinear, and so this will result in a distorted sound. So we can also look at that pictorially and look at that graphically, and let me show you how that might look like. Here is the IV relationship for the export dweeb. So this is my usual relationship. ID equals A e raised to b Vd. Okay, since I picked the export dweeb, it's the same relationship that you've been looking at so far, and Vd equals Vi because the two nodes are the same. So this is my transfer function. So let's take a look at how the distortion comes about if I apply some input to Vi some kind of input. So let's say, for instance, I apply a sinusoidal input where Vd equals Vi. Okay, so I apply a sinusoidal input here. Okay, so this is my sinusoidal input. So that's Vi. So if I apply the sinusoidal input, let's try to figure out what the output looks like. Let me show you a rather stylized way of computing outputs given a transfer function. Okay, this is a little bit of a construction that I find very useful. So what I do is I take this. This is Vd here. So I take this curve and I translate that and light on its side like this. So I get Vd making traversals like this, and this is my time axis. So this is my Vd axis. So I make Vd parallel to this axis, so I can now see what happens when the voltage Vd varies and how it relates to the transfer function curve between ID and Vd. Then what I do is to look at the output. Let me go ahead and place ID out there, and my claim is that ID is going to look like this. Note that this ID is completely different, looks completely different from Vd, and I'll show you in a second why that is so. And that will result in distortion. So given a Vd curve like this and a transfer function given by ID versus Vd up here, let's see how we can plot how the output looks given various values of the input. So let's start. So supposing I have an input right here for VD. So let's start with a point here. Let's see what the output will look like for that point. So I go up. So I look at I go way up here, and for this value of VD, notice that the current is going to be out there. Okay, so for this value of VD, that is going to be the current, and so I can go ahead and plot the current at that point out here. Okay, so at time t equal to 0, which is here, and time t equal to 0, which is here, my current is going to be this. So let me mark those points. So that is let me mark them as A, B, C, D, E. So that's A, that corresponds to this point on the transfer curve, on the IDE curve, and let me mark that as A here as well. Now let me pick the second point and see what happens. And so that second point will result in that is the voltage here, and that will result in a current that is given by this transfer curve out there. And then I can move it over to the ID side. So notice that for this value of time, I get this point in the transfer curve, and I get an X here. Okay, so that's my point B. Okay, so my point B, and B are all the same. So for input at point B, I get a current given by that. Okay, I can take another point, point C, and take a line up, and so it corresponds to this VD, and that corresponds to this value of ID, and so that corresponds to this point in time. So notice that it's this point in time, which is about this point in time, and this is my point C. So ABC on this curve will translate to ABC on the current curve out there. So notice that when I got something like this, in this case, I get something that looks like this. And notice, of course, that for values that are negative, for these values, I get this part of the curve. And the reason is that if you look at, let's say, for example, I pick a point here, and I take a line up here, then this is the current, which is a slightly positive value. The time point is here, and so the time point is here. So this current will relate to this value here. Okay, so so if I call that A, B, C, D, then this is D, and then this will be my point D. Okay, so notice that there's a lot of distortion happening here because my device cannot go down negative. It can only have positive values. Okay, so as you can see, I'm getting a distorted output ID that doesn't look anything like the input curve, the input sinusoid, and so I end up with a ID curve that looks like this, which is quite distorted. So what I'd like to do next is show you a little demo and use a garage door opener LED device and try to pump music through it, and you can see distortion for yourself. And in today's class, we will stop with the distortion, but when we go to the next sequence, we're going to do some magic. Okay, some pretty spectacular magic, and by doing that, we will come upon the next big aha in 6002X, where I'm going to show you how we can actually transmit music and pretending as if the circuit is linear, and you will get a linear response. And by the way, the reason we want to do these sorts of things is that there's a lot of nonlinear devices in the world that have very interesting properties. So, for example, light-emitting devices are nonlinear, but oftentimes they want to convert electricity, an electrical signal, into an optical signal. And so, therefore, I really want to use these nonlinear devices. But then, they're nonlinear. How do I get linear responses out of them? And there comes the small signal trick. All right, let's go to the demo.